The floor is yours.
Thank you very much. So I'm here today to give a brief introduction to IP address management using NIPAP, also known as the best IPAM in the known universe. I'm Kristian Larsson. I work for Deutsche Telekom, specifically within the Terrastream project. I am, however, not representing German interests in this talk or here today. In fact, most of the code for this project was written a couple of years ago during my time at my previous employer, Tele2. So this is me on GitHub. I'm the kind of main contributor to this project. The other guy over here, an ex-colleague and friend of mine, I tried to have him here today as well, but he has a kid, so that didn't happen. Okay, so here's the agenda. I know how everyone loves a good demo and some hands-on, so I am not going to start with that. Instead, we're doing a bit of background, motivation. I want to talk a little bit about the underlying issues and the motivation that drove us into this, and I think that will help you understand why things look the way they do today. Then we'll do a demo, after which we'll go back to a bit of dry theory. We'll look at the design of the NIPAP system, and after which I'll also talk a bit about integration, there's an API, and so forth. If you have any questions, I'd like to encourage questions, and feel free to ask throughout. If it's a broader or bigger topic, though, we might hold it off till the end. So what were the issues that we tried to solve, or the issues that we had and that we tried to solve, and what key functionality did we look for? And first out is data consistency. Back in 2008, 2009, when we started looking at this, at Tele2, we had a number of systems in use. It ranged from basic text files to advanced text files and Excel sheets. There were actually a couple of IPAMs in use as well, but they were lacking in various aspects. So let's not focus on that too much. I think the issue with text files or Excel sheets is fairly obvious. You don't have any form of syntax validation at all. It allows you to write octets in an IPv4 address with a number higher than 255. You can write a 5-octet IP address. And yes, this is something that I've actually seen in real life. And it's easy to laugh at this as a network engineer, but you have to remember that the people that were using these systems, the users, there were many, and they came with a wide range in knowledge and experience. So here's a classic, the Excel drag to extend, right? I mean, you fill in a number of, a little bit of data, you select that, and you drag in the little corner, and whoops, all of a sudden you're outside the boundaries of IPv4, which is right around here, right? I've also seen another instance of something similar happen while the network planners in question did manage to get valid addresses out of it. They just dragged and extended, and all of a sudden they were outside of the allocation that was given to them. So while a valid address, we ended up with collision in the actual network. So syntax validation, consistency checking, that was the very basic requirement, right? And I think that any IPAM that you look at, you'll get this. That's very basic functionality. And back then, we didn't set out to write our own. We were actually looking into what already existed out there. And the key kind of requirements, the functionality that we wanted was pretty much this. So in addition to the basic of data consistency, we wanted VRF support. We wanted proper IPv6, obviously IPv4 as well. We needed scale. I mean, this is a service provider, so we had lots of prefixes, and I'll talk more about that in a second. Last, and certainly not least, is the integration with other systems. We had a bunch of different, you imagine the OSS stack, and you have a bunch of different systems. You want to kind of, spread this information throughout. So integration, that was a key thing. Of all the IPAMs that we did try out, and I should say my memory is somewhat vague on this, some of the requirements were met. I mean, maybe they had VRF support, maybe they didn't have IPv6 or the other way around. But one thing that we often saw was the scaling factor, when you have a lot of prefixes, you end up with like an enterprise IPAM. You have a nice little tree thing where you're supposed to navigate through your prefixes. And when you're in the tens of thousands or hundreds of thousands of prefixes, that becomes rather tricky. So how do you navigate large amounts of information? And similarly, when you're trying to get new addresses out of your system, how do you do that? And often what we saw is like, you do the same kind of navigation through this little tree, you find a free prefix, and then you're supposed to like, oh yeah, I'll take this one. So they're kind of intertwined with the navigation. And right around here is where we start with the demo part. All right, now we're probably going to run into more technical issues, right?
You want the display to be mirrored?
No. Can I do this? Woohoo! Oh, this is awfully small.
Kristian, that screen is easy to look at.
Oh yeah. Job told me about this, but I never caught on. Can you see any of this?
No.
Okay, so it's a little bit. Oh, someone actually went ahead of my talk here and typed in something. Okay, so this is the basic interface of NIPAP. So we'll see we have our VRFs, we have prefixes, and we have pools, and I'll get back to pools in a minute or so. So this is kind of how we tackled navigation. Just like the internet is vast, it's huge amounts of information. How do we navigate that? We search, right? You have Google. And while we didn't re-implement Google, we did, build in a search function, which I'm actually rather proud of. And to top it off, it's recently been improved. That's not in the stable release yet, though, so I'll refrain from talking too much about that. So when we search, we can search for an IP address, like, oops. Great start. All right. So when we're searching for just an IP address, the result that we'll get back is all the prefixes that contain this address. So there's a query interpretation right around here that actually tells you that this is a prefix that the result that we're getting are prefixes that contain this address. And we can see in the list here how this is the NIPAP demo page, by the way. So lots of people have used this and filled it up with crap data, kind of. So, but we'll see here how we have results from different VRFs, all in the same page. In addition, we can. If we instead try to search for a prefix like this, so we're adding the prefix length, we'll see that what we're matching up is everything that is contained within this prefix. In this case, it's far fewer. Still, two different VRFs. We can look at this one, for example. We have a prefix up here, which is actually outside of this, but it's included to give you context. So it's rendering this little tree thingy to give you context and understand the result. Next up is tag, or tags. I'm there again looking. Okay. Any system, containing large amounts of information, you usually find it, that tags or labels can be pretty useful to organize your data. And NIPAP supports this as well across VRFs, prefixes, and pools. So in addition to the results in different VRFs, you also see that we get IPv4 and IPv6 information kind of in the same view. For anything that's not a tag or a prefix, we can search just kind of free text. So this is actually regular expression, and it will match on a number of the attributes of a prefix. So we'll search in the description, we have the node, there's a comment field that's not shown by default. And naturally, we can combine these. So if we want to search for NLNOG and we want to make sure that it's within, let's say, 1018, like this, right? And we only get that result. So per default, or no, not per default, the way it looks today is that the search terms that you have, they're combined together with a Boolean AND operation. And this is one of the improvements that's coming along. It's in Git Master now and coming in the next release, that where you can actually specify the operator. If you type an OR here today, that will be interpreted as a literal OR. So yeah, not that useful. I think that concludes the part about navigation here. Let's see if I can bring this up. And to try to avoid embarrassing myself by my apparent lack of multitasking, I've recorded this so I can speak while it's playing. This is very small. Okay. Okay. That didn't turn out too well. This isn't actually full screening it. Okay.
Maybe zoom in on the page and then try playing it.
Getting there. This is the only, no, you have screens back there. Can you read this? It's awfully small. All right, good. Nope. Okay. All right, so here we are. We're adding a prefix using the CLI. We're just specifying the prefix. We have a type. We set a description, and then it's added. Next up, we're creating a pool. We're naming it link networks and giving it a small description. Then we're setting the default prefix lengths for IPv4 and IPv6 being 31 and 126. That kind of makes sense as this is for link networks. Then we're associating the prefix with, this is on my dev laptop, which is, by the way, why you get that little error there. Ignore that. So we're associating the prefix with this, with the pool. And once we've done this, once a prefix is a member of a pool, we can then go and request. So next time we want a prefix, we want to set up a new link network. We'll just go and request a network from the pool. So this is what we're doing here. We're specifying, we want IPv4, we're saying from pool, and then specifying the name of the pool, setting a description, and hopefully we'll get something back. It will follow all the defaults that we already set, so once you're like requesting from a pool, you don't have to think too much. You know what you want, and then you request it. You can, if you want, specify, like in this case, you want a slightly bigger network. You can specify the prefix length manually. See if I can catch up. This would have been faster if, well, this is faster than if I had typed it. Anyway, so here we can see the result. We see the first one, the second one. Obviously, they fall correctly on bit boundaries. The first is a /31, second is /30. There's a little bit of a gap in between. Now, in addition to IPv4, of course, we can handle IPv6. It happens much the same way as IPv4. We just put in an IPv6 prefix here instead. A little bit slow. Sorry about that. Once we have associated both IPv4 and IPv6 prefixes with a pool, we can start requesting not just IPv4 or IPv6 from the pool, but do a dual stack allocation. And that's what we're going to see up next here. I wonder if we can speed this up.
That's fine.
It's fine. It's so small, maybe you need to catch up, kind of. All right, there we go. Both IPv4 and IPv6 from the same pool. And this is obviously quite useful. The way you register host information in NIPAP is that, with a linked network like this, you don't try to cram in. With a linked network, you have two ends, right? So you don't try to cram in the information of this device being connected to this device in the description of that linked network. Instead, you actually register the two hosts, which is what we're doing. And this is actually kind of three operations normally. You add the linked network, and then you add the first host, and then you add the second host. To get kind of a shortcut, we have this command called add host, where you can actually specify this. So it's a little bit of a time saver. So especially when you're doing both IPv4 and IPv6, which would be kind of 6 operations, we're doing this in just one command and getting all of this. And we can look at the results here, how you have this linked network for IPv4 and this one for IPv6. There's also tab completion through all of this. So that's kind of a nice feature. Makes it fast to work with. Let's see if this works again. Excellent. Okay. Basic design. These are the kind of the basic parts of the system that make up NIPAP and kind of how they're connected to each other. We have the database at the bottom. On top of that, NIPAP-D, which is the NIPAP daemon, that exposes an API for all clients. Per default, we're shipping a CLI. We have a web interface that are all interacting through the API. And perhaps if you want to integrate one of your systems, this is kind of where you'd pick to connect it into the NIPAP system, right? And I mean, this was very important. This was the whole API thing. That was a key aspect. We didn't want the API to be a second-level citizen, if you want. But it was the only interface. So, but looking at the database, and database is in combination with IPv6. This usually causes an issue, and I just love this. You see so many IPAMs or other systems that try to store IPv6 in a database, and they just fail miserably. IPv4 isn't much more than a 32-bit number. It's easy to store. You have an integer in your database, you store it. Even if you're trying to store it as a string, that will, in most cases, work out fine, given the prevalence of the dotted quad format of IPv4. You do a bit of basic input validation, and then you're off fine. With IPv6, on the other hand, it becomes much more tricky, right? Or much more interesting, because we have 128 bits. And not a lot of database systems out there support storing 128-bit integers. There are some suggestions, if you look at, just search for it on the internet, on how to shoehorn IPv6 into two 64-bit integers. Not the best of ideas. The other one, fairly obvious, in enterprise environments, I've seen this a lot. You simply store it as a string. Now that comes with a whole set of problems. Because unlike IPv4, where you have pretty much one format, IPv6, you have a lot of ambiguity. You have upper lower case, you have zero compression and leading zeros. So when you compare these, what prefixes are the same and what aren't? If you're trying to do more advanced lookups, this becomes even more difficult. So NIPAP is exclusively using the Postgres database. I received questions if NIPAP can be ported to try to use MySQL, Oracle, or some other database, and the answer is simply no. And this is because we're relying on features that exist in Postgres. Postgres has a built-in data type that can store IPv4 and IPv6 information. In addition to that, there's an extension called IP4R that allows you to build indices on top of this, including the prefix length information. So you can do very, very fast lookups, and this is what powers the search function. Without these, we wouldn't end up with NIPAP the way it is today. So that's why we're using Postgres and won't be switching away from it anytime soon. As I mentioned, early on, API was a key aspect. There would be no shortcuts past that. I mean, you see other systems, Django, I believe, interacts directly with the database. You have an API, but these are different code paths. We didn't want that. We wanted everything through one, so we could use one code path that would be used and tested a lot. So this is where the NIPAP daemon comes in. It communicates with the database. It's a fairly thin layer, although it does add some kind of intelligence in between. And it exposes an XML RPC API. And I know I probably should mention something about JSON here. I think that's if you're designing an API today, JSON is probably where you'd end up. This was, a bunch of years ago. A lot of the systems within Tele2 were communicating using SOAP, and a lot of push to get SOAP on this. We never even considered that. We wouldn't touch SOAP with a 10-foot pole, right? But XML, SOAP is XML, and XML RPC was the closest but sane option. And I think that's ultimately why we ended up with XML RPC. And in the end, I don't think it matters that much, actually. There are plenty of good parsers for both JSON and XML in any modern programming language or platform today. So that's that. To further make your life easier, if you want to integrate, you don't have to speak with the API directly. There are a few client wrapping libraries that you can use. So there's one for Python called NIPAP. This is the one used by the CLI and the web interface, since those are written in Python primarily. Obviously receives lots of testing, good feature coverage, all of that. Next up is NIPAP, which is the Java library. This is also in active use. I think it's lagging behind just slightly on features. It's one or two features that are kind of missing, but it works well. I've successfully used this to implement something I call NSO NIPAP, which is integration or service for tail FNCS, if you're aware of this system. It's called Cisco NSO these days. It's a provisioning system of sort provided by Cisco. Last and least, NIPAP. So this is a library to communicate with NIPAP from within an Oracle database. Don't even ask how we got there, but it's there. So if you're crazy enough to want to do that, then it's there. So I'm running low on time. Just want a few quick examples. If you want to start out with this, I recommend the Python library. I'm a Python person. There's a boilerplate in the Git repository that you can use that helps you do all the boring parts, like set up an API connection with a bit of credentials and stuff like that. Once that's out of the way, you can get to the fun stuff. I've included 2 code snippets here. It's fairly easy. I think anyone familiar with Python or any object-oriented language will understand this right off the bat. We're creating an object P, right? It's a prefix object, setting the prefix, the type, description, saving, at which point, the client library will start communicating with the API and actually save this to the backend, right? Second one is for searching. We're calling a function called Smart Search. This is the same function that is being used by the CLI and the web interface to provide the search functionality. So it interprets the query in the same way. In this case, we're searching for the tag NLNOG and the prefix, iterating over that and printing everything that matches, right? There's also another, you can write your queries using more of nested dicts in Python, which more of the programmatic approach. This is more for humans, if you will. So, for anyone that want to try and use this, we have the demo page, which demos the web interface. You can reach that at this URL. We have the official web page where you'll also find installation documents. I should apologize to anyone not running Debian or a derivative of Debian. The installation procedure is very slick and smooth for Debian. You'll get these little prompts. Do you want to install into the database? Blah, blah, blah. Yes, yes, yes. It's all working. If you're on any other system, it's a little bit more complicated. But, Debian person, so that's why it ended up like that, right? All the code hosted on GitHub. We're using Travis CI for continuous integration, and this is actually testing the whole Debian, when you were building packages, the whole procedure and doing upgrade testing. So it's fairly advanced. Reference, kind of developer reference documentation is hosted on Read the Docs, and there's also a Git book for user documentation. I have to put the slide in here. No, but seriously though, I'd like, kind of hat off to Tele2. I mean, most of this, 90% or whatever, was developed during my time at Tele2. They allowed the project to become open source. I think that was a nice touch. It wasn't that common in the company at that time. And of course, the development time. It was paid time for me and Lucas, the other guy. So, they pretty much sponsored this whole thing. And on the topic of how to pronounce it, the knights that say ni pronounce it NIPAP. Feel free to pronounce it however you please, though. All right, thank you.
Thank you. Before we dive into the questions, what is the word in English?
Do it in Dutch.
At Koloklu, we've been using NIPAP for, I think, the last 1.5 years. And I want to elaborate on how much time it is saving us. We've coupled it with our customer administration to literally to the point where if one of the Koloklu members asks for IP space, we press the button, give me space from the pool assigned for customers, you fill in this size, and everything else after that flows from there. So the reverse DNS is automatically set so the customer can change it themselves. The right database is updated, fully automatic. And it's just a gigantic time saver. And it's free. So I recommend you, if you don't have anything today that runs, if you're using an Excel sheet, switch. Anyway, that was what I wanted to share. Are there any questions for Kristian?
That obvious, huh?
Hi, so you have your own API. Does it also support pushing to other APIs? Or do you have some plugin infrastructure in there?
No, it doesn't really support pushing to other APIs.
Would you consider it?
Perhaps. I think the closest thing that we've kind of looked at is there's actually kind of an experimental branch where there's NIPAP will anything that happens. So when you add a new prefix or whatever, it's written to an audit log. There is an audit log in NIPAP today. It's just not exposed over the API or anything else. But if you want, you can go in there and check. But it takes all this information, it pushes out over a queue. So that means you'll get an event when this happens, and then you can write your own little script to interact with whatever other API that you might have. And I think that's a very flexible solution, because then we don't restrain ourselves to just supporting JSON APIs or just SOAP APIs or something else like that.
Thanks.
So is this in use at the TerraStream project as well, or is it?
No, not at this time. TerraStream is just a pilot at this point, right? So I mean, it's.
But it needs an IPAM anyway.
It needs an IPAM. It certainly does. This is one of the candidates.
Okay, thanks.
I could just expand slightly on that. So one of the overall. Sorry, I'm taking away your lunchtime now, but I just have to say this. So one of the overall goals of the TerraStream, let's call it the OSS system, right? Is super high availability, and Postgres doesn't meet that requirement. So that's the tricky part in this. If it's going to go into TerraStream, we probably need to do something about that. Fortunately,
Oracle.
Sorry?
Oracle.
Yeah. Yeah. So that's being looked at actually, and there's another interested party in doing this and switching to another database. But that would require major rewrite. So yeah.
No more questions? One last big round of applause. Oh, wait. You were waving your hand?
I was going to say, tell me about the integration with the right database.
Well, that's not a question for you, actually. I'm going to give the microphone to this gentleman, because this is Jurjen from Koloklu, and he actually wrote the integration.
What do you want to know? It's a PHP script which connects to the NIPAP API. I think it runs through cron job once an hour, and then we get all the information, take a look at the RIPE database, see if there are any changes, and then send the changes to the RIPE database.
Is that script available?
Not open source yet. I'm trying to rewrite and make it more useful.
This time I have a question. When you say RIPE database integration, do you also mean routing registry? And are you planning of like doing something with IRR toolset integration?
No.
I could have, there's an official issue on the whole RIPE integration thing, but it's limited development time. You have to focus it. That's not the top priority at this point. So from an official, but anyone is free to do whatever they please, right?
And for Koloklu, the route objects, we have 3 route objects for IPv4 space, and those never change. It's just sub-assignments to the customers that are properly registered to their name. So that's only INET nums. So that's what the integration essentially does. Keep the database up to date in terms of contact details. All right. Thank you so much. Big applause.